Okay. Okay. So hi everyone. Welcome to today's talk. In the last two sessions, we covered the basic topology and also the topological quantum codes. And today we switch gears to the subsystem code. And Derek will giving an interesting talk on this. So let me hand over to Derek. Okay. Thank you.
Hi. Um, yeah, I should share my screen. So, so today I'll be talking about subsystem codes, and we are going to use some of the material from tutorial 3, which is on the theory of stabilizer codes. All right. So let's begin. So as a recap, we will start with a recap of the Shor code, and then we'll discuss what the Bacon-Shor code is. And then I'll introduce what the subsystem code formalism is all about, and then I'll talk about the Bacon-Shor code again, and then I'll do a little summary. So hopefully today's session wouldn't be that long, but if you have any questions, feel free to interrupt, or yeah, just feel free to interrupt. Okay, so the 9-qubit Shor code. So this is the code where we have 9 physical qubit, which is arranged in 3 blocks of 3. So it's a concatenation code where the inner 3-bit repetition code protects against Z errors, and the outer 3-bit repetition code protects against X errors. And so in total, they protect against any arbitrary single qubit error by combining these repetition codes in the concatenated codes fashion. So as a recap, these are the logical qubits of the 9-qubit Shor code. We have the 0 logical qubit represented by this state. So this is effectively the repetition code, the inner repetition code, and then the outer repetition code looks like this, right? And the Z-check operators for this code are given by these operators, these things. So I've arranged the 9 qubits in this 3x3 block. So these first 3 qubits will be these 3, and then these next 3 qubits will be the next 3, and the last 3 qubits will be the last 3 in this block. So over here, the Z-check operators are given by these ones. So in particular, for example, the first two check operators would check whether would look at the first 3 qubits. So the first check operator would check whether the first and the second qubit are the same, and then the second check operator would check whether the second and the third qubit are the same, and this would check if the fourth and the fifth qubit are the same, and that would check whether the fifth and the sixth qubit are the same, and so on. So this would give us the 6 Z-checked operators, and we also have 2 X-check operators. So the X-check operators, if you recall, are going to be of weight 6. So we would have to check the X. We will have to apply the X across all the first 6 qubits, and this would tell us whether a Z error has occurred. Well, yes. So these would tell us if a Z error has occurred across like these 6 qubits, and this would tell us whether a Z error has occurred across these 6 qubits. So that's how the concatenation code works, and the logical operators for this would be given by a column for the Z's and a column of Z's and a row of X's. right? So you could measure, say, the Z operators for the first, fourth, and the seventh qubit, and that would give you the logical Z. And then if you measure the X operators across the first 3 qubits, that would give you the logical X. So I mean, um, we could check this by, say, applying the Z operator. So applying this Z logical operator on the logical 0. So what happens when you apply Z on the logical 0 is that effectively, well, so Z of 0 is 0. This becomes -1. So Z doesn't change this. It changes this to a -1, and then it doesn't change this. Well, so let's look at this. So it doesn't change the first qubit. It doesn't change this 0, but it changes this 1 to a plus, and then it doesn't change this. It changes this to a plus, and then it doesn't change this. It changes this to a plus, and so you kind of get like instead of a 1, you get like a -1 or something like that. And then same for the X. And also you could just do this is also a valid logical Z operator and a valid logical X operator, because you could just so for example, over here, we could say, so it doesn't, a logical operator doesn't change when you multiply by a check operator. So you could multiply, say, this check operator by this guy, and this guy. And then you see that you get this guy. And the same for this guy. If you multiply this logical operator by the second X check operator, you get this. So this is kind of like a more symmetric version of it, but in practice, if we want to, well, compute the logical operators, it will be easier to just compute it in like a single row or column. And this is a 913 code because there are 9 physical qubits. There's 1 logical qubit because an X and a Z operator would together give like a logical qubit, and then 3 being the distance, because that's the minimum weight of a non-trivial logical operator. So this guy has weight 3 and this guy has weight 3, and we could see that no matter how we multiply, say, this Z operator by any one of these guys or any number of these guys, we see that there would at least be 3 3 non-identity operators. So it's going to be of weight 3. And same for this guy. Any questions? Right, so moving on. So let's talk about this 9-qubit Shor code. So these are the check operators that we saw on the previous slide, with 6 Z check operators and 2 X check operators. And so there is a little bit of an asymmetry because there are 6 Z check operators and they are all local. They are weight 2. And then the X check operators are pretty high weight. They are weight 6. They are spread across an entire row or column, like 2 rows. And we could correct X errors. So these Z operators could correct X errors as long as each row has at most 1 X error, right? Because if let's say the first row has 1 X error, let's say on the first guy there's an X error, then this guy would flag this thing would give it a measurement of -1, and this guy would give a measurement of +1, because the first guy is affected and this is the identity, so it's not affected. And so this will allow us to detect an X error on the first guy. Same if we have an error on the second guy or the third guy. So these 2 operators would tell us if an X error has occurred on the first row. these two operators would tell us if an X error has occurred on the second row, and these two would tell us if an X error has occurred on the third row. But on the other hand, for Z errors, we would only be able to detect it using these things, these two operators, and we could correct the Z errors, but only if they occur on the same row, right? Because if you have two, well, so technically, if you have two Z errors on like the same row, effectively no error has occurred. Because I mean, if you look at the, if you go back to the code itself, if you see that if two Z errors if there are two Z errors on the same row, then you see that effectively the code doesn't change. Yeah. And right. But if three Z errors occur on the first row, then it's equivalent to one Z error because two of the Z errors will cancel out. Yeah, so if a Z error occurs on the first row, then this guy would flag an error and this guy would not. If a Z error occurred on the second row, then both of these would flag an error. And then if the third row has a Z error, then this one will flag an error. So there's a little bit of an asymmetry going on. So one could ask, can we kind of make this code more symmetric? So for example, we could try to combine the Z check operators. So we could combine. So here we have the X operators across two adjacent rows for both of these guys. And why don't we try combining the Z operators in the same way? So we combine the first, the third, and the fifth Z operators to get this guy. And then we combine the second, the fourth, and the sixth Z operators to get this guy. Right, you just multiply them together. And now we have 4 check operators instead of these 6 check operators. So what do we get? So these are the check operators we have. So I call this modified Shor code. It's not standard terminology. So what are the logical operators for this code? So the logical operators will be anything, well, which kind of commutes with these check operators. So what are the things that commute with these check operators? So we see that this guy would commute with all the check operators because, for example, these two, well, so this guy would always commute with anything with z's in it, and it commutes with this operator because they overlap in an even number of spots, right? Because this z will anti-commute with this x, and this z will also anti-commute with this x. So in total, they will commute. And so this obviously commutes with this because z commutes with the identity. So this guy commutes with all 4 check operators. So same for this x, because if you, again, it commutes with both of the x's, obviously. And it commutes with the second guy because those 2 spots are just the identity. And it commutes with the first guy because they anti-commute in 2 spots, which means they commute because 2 is even. And well, you could check that the same is true for all of these operators. So you have all of these as operate. Well, so I kept these ones because these ones were logical operators before, so they should be logical operators now because they commuted with the stuff that we had before, and now these things are just products of the operators we had before, and if it commutes with everything else, if it commutes with the things you are multiplying with, then it commutes with the product. Right. So the reason why I wrote it this way is because we noticed that, well, so these two anti-commute with each other, right? Because this and this overlap in like one spot. Well, the x, they differ. They have an x and z which differ in one spot, and then the rest are the same. And the same for the second pair. They differ in this spot, and then the third pair and the fourth pair. So these are, and then you could check that. Well, so you could check, for example, with for the first operator that it anti-commutes with only the second guy, and then it commutes with the rest. And then you could, yeah, and you could and you should check this for all of these. So this would present us with kind of 5 pairs of logical operators, right? So this forms an XZ pair. So this forms a pair of anti-commuting operators. These two would form a pair of anti-commuting operators, and so on. So now we have 5 pairs of anti-commuting operators. Well, and each of these would commute with each other. And so this is so now we have a 9-qubit code again, and it has 5 logical qubits because we have 5 pairs of logical operators, which kind of makes sense because we have 4 stabilizers. So these are the stabilizers, right? The 4 on the top. So 9 minus 4 is 5. So we should expect 5 logical operators, and we found all 5. And so what is the distance of the code? So the distance of the code is the weight of the minimum weight of a non-trivial logical operator. So you look at all these operators over here, and you see that there are logical operators of weight 2. So these, an operator like this would cause a change in the code, right? It would change the kind of the logical information in the code. So it would be considered an error if it was not like an intentional operation being applied to the code. So you could check that this is the smallest possible if you try doing any multiplication of any of these logical operators with these check operators up here, you would always get at least 2 of this of the 9 qubits being not the identity. So the distance of this code is 2, which means it's not error correcting because in order to be an error correcting code, the distance has to be at least 3, right? Because the number of errors it could correct is like the floor of like d, which is the distance, minus 1 divided by 2. But it is an error detecting code, as a remark. And also, this is, it is an error detecting code, but it is a slightly problematic one because the check operators are of pretty high weight. So they are of weight 6. If you look at these check operators, we have like these weight 6. All of these are weight 6. Which means that in practice, when we try to perform the measurements for the checks, the circuit is going to be more complex. It's going to be deeper, which means there is going to be more possible opportunities for errors when we do the measurements, which is not what we want, because the whole point of doing all these measurements is to correct errors. So we don't want to introduce more errors than we correct. And so the question is, can we reduce that weight? And well, kind of the spoiler is yes, we could. And the idea is to measure some of these logical operators. So, one problem of this code is that the weight is small. Well, the distance is small. So we could instead try to measure these operators instead, right? We could measure these operators and then leave these as like the kind of logical operators. And let's see what we get when we do this. Well, before I continue, any questions? No? Okay. So, yeah, so let's see what we get when we try to add more check operators. So this is what we call the Bacon-Shor code, or specifically the 3x3 Bacon-Shor code. So the stabilizers are what we have from before, these 4 stabilizers. So these are the check operators from before, right? These check operators. And what are the actual check operators we want? So the actual check operators we want would be we will add in the logical operators from before. So remember we said that instead of letting these be logical operators, we would add this into our list of checks. So we would measure this as part of our checks alongside the ones that we already are checking. So we have all of these check operators, and then the logical operators will be the actual ones that are left over from a computation from before, which is these 2, or it could just be these because for example, again, you could take this logical operator and multiply by this second guy and you could get this first guy. And same for this second guy, you multiply it by this last guy, and then you get this. Right? So we have all of these check operators, and then these are the stabilizers, which are part of the check operators. But instead of having to check, so these check operators are kind of nice because most of them are weight 2, but you have all of these like weight 6 ones, which we could actually kind of simplify. And why could we do that? Because if we look at this guy, in order to get this guy, we need to measure like these first 6 z operators on the first and the second columns. But we already have this, so this guy and this guy this guy measures the first and the second qubits. This guy measures the 7th and the 8th qubits, which means in order to get this guy, all we have to do is to measure the middle 2 guys, and then, well, in principle, we could just multiply with the other 2, but we don't actually need to, right? Because what we want to say is that it is like stabilized by this guy. So we could derive this guy from the other 2, and same for this guy. So this could be obtained from this third operator times this second to last operator on the first row, and the middle 2 and the 5th and the 6th qubits, 5th and the 6th z operators. And so we could do the same for the x's. The x's, so for example, with this x, you could take this second x operator, this fourth x operator, and all you need to get this operator is to have the x2, x5, so to speak. So like the second x operator and the 5th x operator. So that would reduce our check operators to be something like this, which are all weight 2 checks. So these are good. With the little problem, so-called problem, that they are not commuting. So typically for a stabilizer code, all the check operators are commuting. But here we have like this pair of anti-commuting operators, this pair of anti-commuting operators, and so on. So we have anti-commuting operators in our check operators, but it turns out to be not a problem, as we will later see. And so what this is saying is that this is what we call a subsystem code, a subsystem stabilizer code sometimes. And so we have 9 physical qubits. We have 1 logical qubit given by this pair of logical operators. And then we have 4, which is the number of gauge qubits. So this is going to be a bit tricky to kind of compute. So what happens to get this 4? Basically, it was obtained from over here. We said that we were going to measure these 4 pairs of logical operators. So instead of a 952 code, the 5 logical qubits, we keep 1 logical qubit, and then we measure the other 4. So that's where the 4 came. That's where the 4 comes from. Right, so it's effectively these 4 pairs. And then 3 again is the distance of the code, as you would see. I mean, yeah, because it is basically the again the minimum weight of a non-trivial logical operator. So again, we are not looking at the check operators. We are looking at the logical operators, and the minimum weight is out of weight 3. And yeah, so the upshot is that we get lower weight check operators. And so these are the stabilizers, and these are the check operators. So now all of these check operators are weight 2 instead of like weight 6 for the Shor code. And so in order to get the error syndromes, so in a stabilizer code, what we want is to measure the kind of the errors. We want to make these measurements, but these check operators are not these stabilizers. So we need to somehow combine the check operators in a way to get these weight 6 operators, but it's possible. I mean, effectively, that's how we derive this code, right? So for example, in order to get this first stabilizer, what we would want to do is to compute, well, so we need the first, second, fourth, fifth, 7th, and 8th Z operators. And this can just be obtained from this guy, and also this guy, right? So these three operators, when we multiply them together, we will get the result which we want. We will get the equivalent result of measuring the first stabilizer. And it is possible to do this for so we have three other stabilizers, and I'll leave it as an exercise for you to figure out how we would obtain the other three stabilizers from these 12 check operators. So effectively, these 12 check operators will be split into, I guess, 4 groups of 3 operators. And then you could measure these groups of 3 in order to get the stabilizers, the result from measuring the stabilizers. Right? So now all we need to do is to measure with 2 operators instead of with 6 operators, which is a lot easier to do, like in actual quantum circuits, and then it's a lot faster, and then the circuits are more shallow, so you get better results. So now let's go back to the on the Hilbert space level. How does this Bacon-Shor code work? So there are 9 qubits, so the entire Hilbert space is going to be the complex space of dimension 2 to the 9, right? Because there are 9 qubits. And so in the Shor code, in the 9 qubit Shor code, we have one logical, so this is it. We have one logical qubit. So the logical subspace, which is the first entry over here, is C. It's the complex space of dimension 2 to the 1. So I mean the 1 is omitted here, but 1 represents the one represents the number of logical qubits. So we have 2 to the 1. That's the logical subspace. And then this is just the rest. So this is kind of like the orthogonal complement, or like basically the space that's orthogonal to this C2. And so a stabilizer code would effectively project will project your code back to this logical subspace. So that's how the 9 qubit Shor code works. And the 952 code, which is a stabilizer code, has 5 logical qubits. So it's effectively given by this. So the logical space now is of dimension 2 to the 5. And then the rest of the space is dimension 2 to the 9 minus 2 to the 5. Right? And so what about the Bacon-Shor code? So the Bacon-Shor code is obtained from this 953 code. So if the structure is going to be almost the same as this guy, but within the logical subspace, what we did was that we kind of threw out for 4 of the logical qubits, right? We said that these 4 logical qubits, we would just measure them, and then it doesn't really matter what the individual results are. All we care about is like the products of those stuff that we measure. Those four groups of 3. So effectively, the 4th logical qubits that we threw away, that would form this guy. So previously we had like a direct sum, and here we have like a tensor product of spaces, where this first component over here would represent the actual useful logical information that we have. So it's what we call the logical subsystem. And then this guy would be kind of like the stuff that we are not so concerned about, because we are okay if this stuff is like not preserved. All we really want to do is to preserve this guy. So this is the Bacon-Shor code. Any questions before we continue? No? Okay.
Yeah, I mean, you can unmute yourself and ask if you have a question. But yeah, I mean, awesome tutorial so far, Derek. Yeah, I think it's clear. Maybe that's what people are not asking. Yeah.
Extremely unclear. People don't know what to ask. Yeah, okay.
Maybe can I ask a question?
Sure.
So the logical space is never measured, right? I mean, these 4 subqubits, right, of the subsystem code.
You mean this 4?
The 4, right? You have the one that's truly preserved, and then the 4 the gauge qubits, right?
Yeah, these are the gauge. This is the gauge subsystem. Yes.
So do you actually measure them? Like after doing a pseudo measure, are they measured, or you just don't interact with them?
Yeah, I mean, you could. I mean, basically each of the gauge operators would act as the identity here, and then would act as like some strange stuff over there. But it's like not. I mean, we don't track what they do.
Right. So they will just decohere over time.
Yeah. Which doesn't matter to us because we only care about like the first guy.
Right. Okay, makes sense. Thanks.
All right. So we move on to the next slide. And so what is a subsystem code? So a subsystem code is an NKGD code. So D represents the distance, which I didn't define up here, so I just like put it as a footnote. But a subsystem code is a decomposition. So we have n physical qubits. So the entire qubit space is of dimension 2 to the n, and you could decompose it as a kind of this is kind of just like the stabilizer code. You have a space Q, a code space Q, and then a space Q perp, which is the perpendicular or the orthogonal complement of Q. But what's the difference between a subsystem code and a stabilizer code is that this Q will be further decomposed into A tensor B. So this A would have dimension 2 to the K, and this B would have dimension 2 to the G. So K is basically the number of logical qubits, G is the number of gauge qubits. So yeah, so we call A and B the logical subsystem and the gauge subsystem. And so this is, I mean, this is kind of good if you, I mean, if you want to think at the level of Hilbert spaces, but typically we are more concerned with the operators acting on these codes. So we look at the stabilizer code and the gauge, the stabilizer group and the gauge group. So both of these are poly operate. Both of these are contained within this poly group, which is the set of, I mean, tensor products of I, X, Y, and Z, n times with possible plus minus 1 or plus minus I in front of them. So this stabilizer group S is an abelian. So this is exactly the same as in the stabilizer group case, where it's an abelian subgroup of Pn of the poly group, and it doesn't contain minus 1. And well, and the common plus 1 eigenspace of all these operators is Q. So basically, Q is the space of code words where S is the set of operators which fix everything in Q. And G is the gauge group. So this is what's different than the stabilizer group. And so this is where we have a subgroup of Pn, which is not necessarily abelian. And the point is that the center of this subgroup is exactly the stabilizer group along with I times the identity. So S doesn't contain minus I, which means it doesn't contain it doesn't contain the complex this II or minus II, but this G would contain all of these things. So G would contain minus I, and little I times the identity and minus I times the identity. And each of the things in G, so each of the operators in G would act on this Q by the identity on A. So it doesn't touch the logical subsystem, but it possibly messes up the gauge subsystem. But it turns out that we don't really care about those. So we in practice, we would measure both S we would measure like basically things in G. And a stabilizer code will be a special case of this subsystem code where this B is just the identity, which means this B is like a one-dimensional space. So G is 0. And so, so it's like a copy of C or something. So it doesn't really matter. And then, and this gauge group would be exactly equal to this. And you notice that the center of this, so this is going to be abelian, so it's going to be exactly equal to this. So this is kind of like the special case where this is like the special case of a subsystem code. There are a bunch of comments in the chat, which the gauge qubits will be measured when you are trying to measure the syndromes. Yeah, so when we are trying to we are trying to do the error correction, we would measure all the gauge qubits. I hope that answers the question. Okay. Any other questions? No. All right. So what are the logical operators of a subsystem code? So recall from the previous slide, a subsystem code is just defined by a stabilizer group and then a gauge group. And so the logical operators are basically the ones that preserves the code, so preserves the space Q. So they are exactly the things that they are in the normalizer of, so that commutes with the stuff in S. And sometimes you would see people talk about bare logicals and dressed logicals. So bare logicals are those that commute with all of the gauge groups. So these are the logical qubits that don't actually touch the that only act on the logical qubits. So they don't touch the gauge system. And then the dressed logicals are the ones that might touch the gauge subsystem. But in practice, when we say logicals, we really just mean these dressed logicals. So we just because typically we don't care about whether the gauge subsystem is being messed up or not. But this is just something that you might encounter in the literature. And sometimes in the literature, you would see people refer to like the logical group as like NS over. And so NS is the normalizer of S. So sometimes you would see this, they will refer it to as NS over G. And one has to be a little bit careful because this NS over G is actually an abelian group. You kind of lose any like anti-commuting structure unless so this group itself is abelian because G contains minus I, which means when you mod out by G, you mod out by minus I, which means minus 1 is equal to 1. So this group becomes kind of abelian. But there is a way for you to kind of like talk about whether poly operators commute in this if you kind of like impose like a symplectic structure or something, which might come up later or might have already been discussed before. Yeah, any questions? No? Okay. Right, so this is kind of just a little something extras. Sometimes it's easier to think about subsystem codes in this like canonical form or standard form where effectively for any subsystem code of n like with parameters nk gd, you could kind of find n pairs of virtual poly X and Z operators. So these are not the actual X and Z operators, but this you basically need to do some sort of maybe a unitary transform or something like that. And then you would get like this n pairs of, basically you do a change of basis, and to get this n pairs of X and Z operators, which I denote with a prime to say that they are not the actual ones, but I kind of suggestively kind of write them like that in order to like denote that xj and xk primes would commute, zj zk prime commutes, and zj zk prime, xj zk prime commutes if the j and k are distinct. But you would also have this relation where xj prime and zj prime would not commute. And then the squares are all the identity. So I mean, this is really just saying that they have real eigenvalues. And we could arrange such operators in a way that the stabilizer group is just S of the operators over here. So it's like, so the stabilizer group is an abelian group. So it's, I mean, if it's of size S, then, and S is going to be N, so the total number of qubits minus the number of logical qubits minus the number of gauge qubits. So S is just going to be some S, S number of commuting operators, which we just denote by C1 prime to CS prime. And then the gauge group will be given by little I times the identity together with this S. So these S operators could come here. And then we would find another G pairs of like anti-commuting pairs of operators. So this would be kind of the structure of the H group. Okay. I mean, this is kind of like the more kind of canonical, like it's like a canonical form in a way, which you could get to by a unitary change of basis. And then to do the checks, when we do the check measurements, what you would do is to measure all of these guys. I mean, you want to measure all of these guys basically. So these S operators and these 2G operators. I mean, you could also end up measuring like products of these guys and so on, just like we did before with the Bacon-Shor code. And the representatives of the logical groups are just so the logical operators are the ones that we didn't measure. So I mean, basically the ones with indices S plus G plus 1 up to N, which is S plus G plus K. So there are K pairs of these guys. Okay, any questions? No, all right. So one could ask about what about the, I mean, so I guess I talked about the Bacon-Shor code just now, but that was not exactly what the general Bacon-Shor code is. So I talked about 3x3 Bacon-Shor code, but in general, the L by M Bacon-Shor code is, so previously we had like a 3x3 lattice. So here we have an L by M lattice where you have L times M number of qubits. And the gauge generators are just the kind of the nearest neighbors XX and the ZZ operators. So it's kind of exactly the same as previously, except like instead of doing like two pairs, like I mean you have like the vertical axis like down the entire column for each of the columns, but like just pairs of them. So this is kind of the general Bacon-Shor code. And I mean, I guess I'll leave it as an exercise, but you could think about what is the stabilizer group of the general Bacon-Shor code of this L by M lattice? And what is a set of independent generators for this stabilizer group? Basically, what I'm asking is effectively how many, what is the size of the stabilizer group effectively? So you could try to think about what is the stabilizer group. So remember the stabilizer group must be things in the stabilizer group must commute with all the must be kind of like this center of the gauge group. Well, minus the complex I times the identity. And then what are the logical operators of the Bacon-Shor code? So the logical operators are the ones in the normalizer of the gauge group, right? And so how many logical qubits does the Bacon-Shor code encode? And finally, what are the parameters n, k, g, and d of the Bacon-Shor code? So I mean, n, I guess I kind of gave it to you. It's L times m. But so k is the number of gauge, is the number of logical operators. So it's kind of like, I mean, k is the answer to this question. How many logical qubits does it encode? G is the, well, to get G, it's probably easier to kind of compute what the size of the stabilizer group is, and then n minus k minus s, the size of the stabilizer group. Well, the dimension of the stabilizer group of F2 would be equal to G. And then D would be the distance. I mean, again, the distance is the minimum weight of a non-trivial logical operator. So, I mean, look at the logical operators and think about what is the smallest possible operator. And once you have got this, I mean, and then you kind of check it with the case L equals M equals 3 and see if your answer matches that. And so the takeaways for, I guess, this session is that subsystem codes, they introduce gauge degrees of freedom. And in some sense, this would help us to reduce the weight of the check operators. So just like the Bacon-Shor code, we reduce the weight of the checks from 6 to 3 to 2. And the canonical example is just the Bacon-Shor code, because we just have 2 body checks. And yeah, we discussed the subsystem code formalism, what a logical subsystem is, what a gauge subsystem is. And then we talked about the stabilizer and gauge groups. And so for the next session, we will talk about the New-Laflamme condition. So I believe Andrew discussed the New-Laflamme condition in tutorial 3. So we have an analog of the New-Laflamme conditions for subsystem codes. And then we would talk about more examples of subsystem codes. And then more reasons why subsystem codes are useful besides reducing the weight of the checks. Okay, that is it for today. Any questions?
What's the downside of using subsystem codes? They're so much better, right? I mean, you say they have less weight, right? Is there any price
I mean,
to pay?
I guess one downside is that, I mean, it's kind of, in some sense, more complicated. And I mean, for the Bacon-Shor code, I mean, going back to the Bacon-Shor code, which is way back up here. I mean, so, well, so for the 9-qubit Shor code, we could, I mean, in principle, we could correct errors as long as each row has like at most one X error. I mean, so for example, over here, I mean, in principle, even though like the distance is like 3 and we could correct at most one error, we could technically correct like 3 errors, because if one error occur on the first row, one error occur on the second row, and one error occur on the third row, we could in principle correct 3 X errors. But if we go to the subsystem case, then we wouldn't have that flexibility. We would kind of like only be able to like correct like 1 error.
Is this because that's the reason the Bacon-Shor code doesn't have a threshold?
Good question. I do not know the answer to that question. Possibly.
Also, I don't know, maybe one more downside that I can think of, like on the fly, is that, so for a stabilizer codes, all measurements commute, right? So you can also do like, combine them together and do simultaneously, like a smaller number of measurements. But now here they don't commute, so that can be a problem. I mean, it's not a big problem. The weight is small.
It's really a
but
problem because let's
no,
say
no.
in
I mean,
S code, like surface code, you measure like these and X separately, right?
sure,
So you
sure,
can
sure.
do the
No,
same thing also
I'm
with the Big Shor, right?
what I'm saying that it effectively becomes, like 2-round kind of measurement where you have to do like all G and then all X. I mean, if one has to search for, like let's say a problem, then I'm saying. Otherwise, if we think about, like a beacon Shor code, I mean, basically you manage to keep your number of logical qubits same, the distance same, and reduce the weight of the operator. So in terms of parameters, it's like, strictly better than Shor code. But yeah, I don't know, maybe issues like lack of threshold or something. But I mean, like, maybe when we say lack of threshold, it's for the code family, right? I mean, threshold is for family. So you try to come up with a code family starting from Shor code, which is our code, and here you at least get a code family. So I don't know whether it will be a good comparison to say that when we moved from uh, uh, a stabilizer code to a subsystem code, it's the subsystem structure that made us like not have threshold, when already when we were in the stabilizer case, there was our code and not a code family to start with.
So for Beacon Shore code in particular, I think the reason why it doesn't have a threshold is because the size of your stabilizer increases as you grow your patch,
Yes,
right?
yes.
Then you need like more rounds like to measure one stabilizers because you have this bunch of 2-qubit check measurements to measure just one stabilizer. Then as your code size grows, then that's gonna take a while. And then errors can keep piling up.
Right.
So I don't understand. Like,
Because I mean, if you have
this
like
is
this one patch of qubits where you put your Bacon Shor code in, your stabilizer code is going to grow linearly with the size of this patch. If it's like an L by L patch, then it's gonna
I mean,
go
I mean
down,
the exercise
right?
that Derek was saying, like if that, like, I mean, so where there, when you look at the stabilizers, you will see that, it's like it corresponds to 2 adjacent rows. And so the size kind of, increases like, with the lattice on which you are putting it, like L cross M. Yeah. So that's a possible reason. I mean,
but any code
but I
has
don't know,
issue.
there
The
was
service
some
code has the same
paper.
issue, no?
No, in surface code, like your
Yeah.
stabilizers, I
They're
mean,
only 4 qubits, right? No
they're
matter
4 qubit
how
stabilizer.
big you grow it.
Like here your stabilizers are, like, I mean, they increase with I mean, the size of the code family. But
The
on the
weight,
other
no?
hand, so in that
Yeah.
sense, like, if we think
Stabilizer
about
weight.
it, if we think about it, like just QLDPC code, like LDPC code, where let's say we are interested in stabilizers and not checks, then it's not really, like a constant weight stabilizers. Like stabilizers do not have constant weight. Like it is a function of, like lattice size. On the other hand, for the stabilizer codes, sorry, surface codes, your stabilizers are constant no matter what size lattice you go.
Yeah, I should point out another error completely unrelated to this, but a thing that I just kind of worked out is that this Z operator, which I said this was the Z operator, but this is actually the X operator, because when you apply this to the 0, you kind of when you apply this to the 0, you get a 1, and when you apply this to the 1, you get a 0. So this is the X logical operator on this, not the Z logical operator that I said earlier. And this is the Z logical operator. Yeah, but oh yeah, someone has a question.
Yeah, maybe you can unmute yourself and ask. Yeah.
Yeah. Hello.
Hi. Yes, we can hear you.
Yeah. First of all, thank you for this amazing tutorial. I actually wanted to know more about those bare logical and dress logicals. Um, because eventually we will only need the we will be measuring the gauge qubits, so we'll be losing that information. So do we really need the dress logicals in our complete operation, the encoding, error correction, and decoding?
No, dress logicals are what we actually care about, because we care about the operators that preserve the entire we care about the operators that kind of preserve the code. So preserve the queue. So we have a queue, right? So the dress logicals preserve this entire space queue. So it might mess up like A or B. I mean, so messing up A is equivalent to like changing the it's like a logical operation. Well, messing up B is like it doesn't really matter. But the kind of bare logicals are the ones that only change the A. So they change the A, but they don't touch the B. So those logicals are like, those are nice logicals, but we are not that interested. We are not, in practice, we are not that particular. Well, we don't really care too much about them because we don't care if things in B gets changed.
Yeah, that's what. So we care more about the bare logicals which affect A, right?
Yes, the bare logicals affect A, yes.
Okay.
So yeah, I see where you're coming from, but what I'm saying is that the dress logical, so if you want to apply a logical operator, you would probably apply a bare logical. But I guess when we talk about things like distance and stuff, the dress logicals come in because those logicals we cannot distinguish from the we cannot really distinguish.
Okay.
Using just the stabilizers.
Oh, okay. Yeah. Okay. Got it. Yeah. Thank you.
No problem.
Hello.
Hello.
For the Shor bacon code, how to determine where the error occurs according to the syndrome measurement outcomes?
So it's like what we did for the modified. It's like what we did for the almost like what we did for the Shor code, basically. Right? Or maybe the modified Shor code. So for example, the whole point is that with all of these check operators, using all of these check operators, you could measure the outcome of the stabilizers, right? Because to get this stabilizer, you kind of measure this first guy, this this guy, and this guy, right? So depending on the outcome of these three, so if these are like +1, +1, +1, then this is +1. This is like +1, -1, +1, then this is -1, and so on. And then from here, you would know that, if this is a -1, you would know like kind of like one error has occurred. And then if this is a -1 also, then you will know that one error has occurred. Then you kind of know like which row has an error and which column has an error and so on. And same for the axis. So it's very similar like what we did for the analysis for the Shor code case. Does that make sense? Or should I say more? Yeah, so
yeah,
yeah, go on.
Yeah, I'm thinking as the check operators do not necessarily commute with each other, then the stabilizer group of subsystem code is not like that of the stabilizer code 1.
Yes.
Oh.
Yes. So what we want to do is, so for example, to measure this guy, to get this guy, what you would do is measure this first guy, and also this guy in this order. And then, so the order of the checks is somewhat important. So measure these 3 checks to get this guy, and then measure the other 3 Z's to get this guy. And then to get this guy, we would measure this X, as well as this X, right? And your worry is that it might affect this guy. So it actually doesn't affect the value of this guy, because if you notice, this check operator commutes with both of these. So all of these stabilizers commute with all of the checks. The checks don't commute amongst themselves, but the checks commute with the stabilizers. So after you determine like the kind of value of the stabilizer, the value of the measurements of the stabilizers, it doesn't really matter. It doesn't really matter if you like say measure. So if you've determined this to be like a +1, after you measure this, it doesn't really affect the measurement of this because this commutes with that. So when you start measuring the other two, it wouldn't affect the result that you got before. And the main point is exactly because the check operators would commute with stabilizers. That's why we wanted the stabilizers to be the center of the gauge group, right? Because that means it commutes with everything in the gauge group. Does that make sense?
Yeah, thank you.
No problem. Any other questions?
I mean, maybe we can wrap up the session and people can discuss on Discord and so on, because it's already 9:30 something.
Cool. So if
Okay.
there isn't any problem, so we can stop here. Yeah.
All right.
Thank you, Derek. Thank you for a nice talk.
Thank you guys for
See you
listening.
guys next week.
Thanks, Derek. Yeah.
Thank you, everyone.